Hi, in this lecture, we're going to be talking about the mechanics and some of the data structures involved in Bitcoin and try to explore some of the specific details at a lower level than we've been dealing with. So, first, we'll be talking about how blockchains actually store their records. So, we touched this briefly before, but the way that Bitcoin specifically stores records is slightly different from what we might think conventionally. So the way that this happens is every transaction in Bitcoin operates in the form of input output. So in a conventional system where you possibly have say in a bank or an account based system, you would basically keep accounts for each ID. And what you do is you track changes from account to account. So for example, say you had two people, Justin and Stacy. So Justin has an account, Stacy has an account. So you would record a first transaction from Justin to Stacy, where Justin pays Stacy some money, then perhaps Stacy pays someone else some money. In that way, you would store those transactions. In Bitcoin, we look at this exclusively as inputs and outputs. So, for example, in the figure that you see here, um, you have 60 bitcoins coming in into the transaction. There are three transactions that you can see here. So this is one, this is another, and this is the other one. So here you see 60 bitcoins coming in, and this transaction creates two outputs, 50 bitcoins and 10 bitcoins. In the transaction at the bottom, you see 30 bitcoins coming in, creates two outputs, 20 bitcoins and 10 bitcoins. Now, so what this transaction is basically doing is it's taking in some bitcoins, it's distributing them in a different way. Now, remember, each of these transactions are signed by the sender. So here you would have this transaction signed by whoever is the sender, giving money to someone else and possibly to themselves. So these 10 bitcoins could, or these 50 bitcoins could be addressed to themselves. We'll see this later. Anyway, so this is how it takes one input in and produces outputs. Next, other transactions, they will reference these older input outputs when they try to make a new transaction out of it. So for example, in this new transaction, these 50 bitcoins are actually going to be referencing this output here, which produced these bitcoins, which made these bitcoins available to this address. So these 50 come from here and these 20 bitcoins come from here. So we have these references implemented through hash pointers in the blockchain. So what we'd basically do is we'd reference these previous outputs, use them as inputs, and then again make new outputs. Notice that the number of inputs is both variable as well as the number of outputs. So you have two outputs each here, but one input here, and you have several inputs here and one output here. Now, let's take a look at an actual transaction. So this image is from blockchain.info. All the information is readily available on the internet, so you can go there and see it yourself. But we'll just walk through some of what we're going to be dealing with. So basically, this transaction, as you can see, it's clearly represented as an input and as outputs. So here you can see that there's an input address. So this is the sender's money, and these are the addresses in which you can expect the money to be distributed to. Now, one of the interesting details here, if you can notice, so two observations here really. First is that this value that you get as an input is 0.95 bitcoins here. And if you were to add up the outputs, so 0.39, 0.005, 0.0015, 0.55, you would roughly get about 0.95. Sometimes it wouldn't be exactly the same. So even in the previous slide here, we said 60 was 50 plus 10, so you had 60 and 60. This might not always be the same because recall from a previous lecture where sometimes you can have the outputs have less value than the inputs so that the remainder can go as a transaction fee. So it doesn't necessarily have to be exactly equal, so it can be slightly less. So that's one observation. The other interesting observation here is look at the addresses. So the input addresses and the output addresses. So you will notice that some addresses, and specifically two addresses, appear twice. So basically two addresses are the same. So this address appears twice, BC1QW, and you again have BC1QW here as well. So what is happening here? So in the Bitcoin context, all the inputs that you get in a transaction have to be consumed. So you have 0.95 Bitcoins here. So suppose this is my wallet and I have 0.95 bitcoins as my balance. I might not. I do want to give someone else some money, say for some service or some product. But because in each transaction, all of the inputs have to be consumed, it might be the case that I don't have to pay the other person all of my money. So what I can do is I can split up the outputs such that one of the outputs refers back to me. So here you can see that 0.55, in fact, more than half of all of the input is going back to the same address, and the rest of the outputs are addressed differently. So these are all different addresses, but this address and this address is the same. So in this, we refer to in this context as a change address, because the remainder is the change here, and we revert that back to the same address. So yeah, so that's an interesting detail there. Now we'll be talking about so basically the structure of a block in a blockchain in a bit more detail than we did before. So before we get into that, a few terms that we'll be needing later. So a block is basically the basic unit of a blockchain, contains a set of transactions. The parent block of a block is the block that it refers, is the previous block on which this block is building on, and conversely, the child would be the block that will in the future refer our block, the block that we're currently considering. Genesis block is the first block in the entire blockchain. So the header of a blockchain contains a few important details. So there are some other details as well, but I'll just be dealing with a few of the ones that we think is important. So obviously there will be the hash of the previous block. You'll also have something called a Merkle root. We will try to understand this very soon, and we'll get to this. So hang on to this. We'll have a timestamp. We'll also have a difficulty target. So note that if you recall from previous lectures, the difficulty of the puzzle that you're solving in the blockchain context, in a Bitcoin context, so the proof of work puzzle, it changes over time. The reason that it changes is because as things get more powerful, you would eventually start to have more processing. You would eventually have more and more processing power. So what that would mean is these puzzles would be solved faster. So what the system does is it makes these puzzles harder and harder to solve, and it raises the difficulty. So that is the difficulty target we have. It raises the difficulty to make sure that the time difference between blocks being generated is roughly constant. Next, we have the nonce, which is the value that you must arrive at. This value is what, when hashed, will give you the target value. So basically, this nonce proves that you indeed solved the proof of work, so that other nodes can validate the block and believe that you actually did solve the proof of work. So again, from blockchain.info, we have an actual block that was added to the blockchain. So if you look at some interesting details here, so look at this line here. The miners of this block earned a total reward of 6.25 bitcoins. So this value used to be 25 bitcoins. But as we discussed earlier, every 4 years or every 210,000 blocks, the reward that you get for mining halves roughly. So so we went from 25 to something around 12 to something around 6 now, and we expect this to reduce in the future, as we discussed earlier. And instead, as the mining subsidy, as we like to call it, gets smaller and smaller, we would start to rely more and more on the transaction fee itself. So blocks, so we would like to have block transaction fees and fee rewards in that block. So you can see there's a fee reward here as well. So those sorts of other fees will start to become more and more prominent as the mining subsidy reduces. Also, you can see the Merkle root. I mentioned this again because this is very important. We'll be looking into this very soon. So this is a part of that block. And remember how we talked about the block creation, the difficulty target, and how we would like to roughly maintain 10 minutes as the block creation time. So if you look at the time difference between when these are mined, you will see that these are roughly around 10 minutes. So the difference between these two blocks, which have been mined, is exactly 10 minutes. The difference between these two is 15. The difference between these two is around 4 minutes. So it's all roughly around that same area. So basically, we're trying to ensure this is, of course, a random process. So you can't make any exact demands on how you want the time difference to be, but you can keep changing the estimate so that over a large space, when you average out the time differences, those are roughly the same. So how do you identify a block? So what you can do is you can hash the entire block. So the hash of the block would be a unique ID of that block. So note that this is not included in the block structure anywhere. So what happens is when a node is accepting that block, or when a node receives that block over the Bitcoin network, it is computed at that time. So it's computed by each node upon receipt, and you can store it in a separate database table for fast indexing and other sorts of uses. Another block identifier, so the hash of the block is unique. However, we have a non-unique identifier for the block as well, which is the block height. Basically, the height of the block in the blockchain. So you can think of a blockchain as a vertically increasing stack. So at the bottom, you have the genesis block, and as each block is added, it sits on top of a previous block, and then another block sits on top of that block, and so on. And this continues over time. So the height of the block directly refers to the position of the block. So if a block is at height 30, it means there are 30 blocks preceding it. So at the 30th position, you would probably have just one block. However, this is not always the case, as we've discussed. So at certain points in time, there may be several blocks which are competing for the same position in the blockchain. As a result, all of those blocks, because they are being mined by different miners, all of those blocks would hypothetically have the same block height. So it would not be a unique identifier, but nonetheless, it is a reliable way to identify a block, especially for blocks that have been mined long ago, because they are probably in the overall consensus chain by now. So the block height is a good way to refer to that block. So as for storage, a blockchain can be stored as a file or in a database. And so the Bitcoin Core client stores the metadata of the chain in Google's Level DB database. So we'll be talking about a specialized data structure called Merkle trees. So these Merkle trees, they allow for efficient computation when it comes to transactions. Specifically, to prove that a transaction is included in a Merkle tree, you can make that really fast. You can also check if two sets of transactions are the same really fast. So those sorts of things are enabled by Merkle trees, and these trees are heavily used in the Bitcoin network to make sure things go smoothly. So we'll take a look at what these trees are like. So here we see a Merkle tree. Now, what do we have here, and how do we interpret this? So the way to go about this is to consider that we have 8 different transactions here, and we would like to store all of these 8 different transactions in a blockchain block. So how would we go about this? We could serially store all of the 8 transactions simply inside a block, and we could just list them one by one. But we will try to arrange these things in the form of a tree, a tree which extensively utilizes hashing, and we'll explain why this is beneficial. So you see 8 transactions here, A, B, C, D, E, F, G, H. And the first thing I want you to notice is that these transactions are, this tree is computed bottom up. So you have the lowest level first, the leaves of the tree that we refer to in general computer science trees. And then what you do is you build from these leaves towards these middle nodes and finally up to the root. So how do we actually go about this? How do we implement this? So this tree extensively uses hashing, as we discussed earlier. So for example, at the root level, we would take the hash of A and the hash of B. These would form the root, and the hash of C and the hash of D, hash of E, F, hash of G, and hash of H. We take all these hashes separately as separate nodes. Now, a small detail here is that in the Bitcoin context, we actually utilize double hashing. So note that Bitcoin uses SHA-256, as we mentioned earlier. So to compute the hash of A, what we would actually do is we would take the hash of A, the SHA-256 hash of A here, and then again recursively, basically hash on that, or hash on that value as well. So we would have SHA-256 of SHA-256 of A. So we take the hash of A. So similarly, we would do that for each of the other things. Next, so for example, let's go from AB to AB. So how do we go from here to here? So what we do here is we take the hashes of A and B by double hashing, and then to compute the hash of AB, what we would do is we would concatenate the hash of A and the hash of B, as you can see here if you follow my mouse. So we concatenate the hash of A and the hash of B, and then double hash that as well. So take the double hash of this concatenation and then hash on top of that. So hash of A plus hash of B, and then a double hash, we'd get hash AB. We do the same thing for all of for the rest of the tree. So what we do is double hash of C, double hash of D, and then we take the concatenation of these individual double hashes and then double hash that to get CD. In this way, we build up the tree, and then we go up to ABCD, and then finally to the root. Now this root, the final hash which represents all of the transactions in that block or in that set of transactions, this one hash value that we would get, this root is what is stored in the blockchain, as we've mentioned several times here, the Merkle root, as you can see in this real life block of a blockchain, so of the Bitcoin blockchain. So this root basically this root is a way to summarize all of the transactions in that block. So you can see how this is super efficient. So you can simply take a look at that root and use that as a summary. So if you have two different roots which are the exact same, then you can immediately off the bat say that the transactions the transactions represented by them are likely the same. So the set of transactions, we're dealing with the same set of transactions. So a few more small details here. So you have A, B here and C, D here. So the thing that you would have to notice here is that this is a binary tree. Binary meaning that each node has two children. So you obviously can have cases in which you have an odd number of transactions. So in that case, what we would do is we would need it to be a binary tree, right? So what we do is we duplicate the last transaction that we have, so that we now have even number of transactions, which gives us a balanced binary tree. So in that way, we would build that up. So that's just a detail that I wanted to put out there. So let's look at an example of an application of these trees. One very popular example that's used in the Bitcoin network is to prove inclusion. So say we have a Merkle root, and we want to prove that a certain transaction is indeed included in that hash that we get, the final Merkle root hash. So say we have the same set of transactions that we were discussing earlier, so A, B, C, D, E, F, G, and H, and say we wanted to prove that E is indeed in this Merkle root. So we can do that in logarithmic time, so given certain values. So what we would need to prove this is an authentication path. So to prove that E is indeed in this in the Merkle root, what we would need is just a few other hashes. So if we were provided the hash of F and the hashes of G, GH, and the hash ABCD, so these three other hashes, we would be able to very efficiently conclude that E is in fact in this tree. So what we would simply do is we would compute the hash of E, and then concatenate the two, and then compute the hash of EF. We would then compute the hash of EFGH, and then lastly we would combine this with this that we were already provided to finally get ABCDEFGH. And if these two roots match, we have a match. So what are we basically doing? We're just going up one path of this tree, and as we go up this tree, we are leaving out the other halves of the tree. So this gives us logarithmic time. So what we're able to do is we're able to efficiently prove that E is indeed in the tree. So to be able to do this, we would need to have F, GH, and ABCD provided, so that we can correspondingly make the hashes EF, EFGH, and ABCD, EFGH. So these hashes that we would need to have provided, we can refer to them as an authenticating path. So given the authenticating path, it's very easy for us to find out if a specific transaction is indeed in that tree. So to sum up, these Merkle trees are a compact representation of the data. It's faster to send over the network. We can also, to check, as we discussed earlier, to check if two sets of transactions are equal, we can just match the root of the tree. However, if we want to be even more, if we want to get even more utility out of this, if we were to see two hashes which probably vary in just one transaction, or in just one change transaction, we can do that as well. So if two sets of transactions are exactly identical, we would just match the trees, match the roots of the tree. If they are not identical, to detect the different transactions, what we can do is we can take the two sets of Merkle trees and we can just keep matching hashes of the subtrees from the root downwards until you find the change transaction. So here, if we have this tree and if we had another tree like this, if there was indeed a transaction that was different? Let's say E was different in this other tree. So we had E prime instead of E. So as we take this tree and as we go down this tree, so obviously the root will be different because E prime is different. So the other tree will have a different Merkle root. But if we go down one level, ABCD will not be different. This is because E prime, which is where the transaction is different, has nothing to do with ABCD because ABCD is simply a hash of the transactions A, B, C, and D. Therefore, this would be the same. So immediately we can cut out half of the search space and we wouldn't need to look at the left. We would now focus on EFGH. Now, looking at EFGH, of course, this is different because EFGH contains E. So in the other tree, which has one transaction which is different, E prime, this would be different because this contains E. And that tree would contain E prime here. So what we would do then is we would go one level down now, and then we would check EF and GH. And we can be sure that GH isn't, we will find out when we inspect these two trees, we'll see that GH is the same in both trees. Because, of course, the corrupt transaction or the transaction that has been changed is not under the subtree of GH. Again, we leave out half of this search space and we basically look at only EF. And then from EF, we can efficiently find out that E is indeed the transaction that has been changed. So basically, at each level, we are skipping half of the tree, which again helps us to find out the different transaction in logarithmic time. So yeah, that's another way in which we can use Merkle trees to make things efficient and to make these comparisons very efficient in the Bitcoin network. And lastly, just a summary of what we've discussed and how the Merkle tree really fits into the block. So we have a blockchain block here, and the block header contains some. This doesn't represent everything that the block header contains, but just some of the important details. So we discussed already. It contains a hash of the previous block. Basically, its parent. It contains the nonce, and in the block header, we already have the root hash. Now, the root hash is basically literally the tip of the iceberg. So you have the root of the tree in the header, but the rest of the tree is also stored in the block. So you have the other transactions as well. But for quick and easy comparisons, especially if you establish the two trees are the same, you can just look at the root hash. Yeah, so that sums up Merkle trees and the important data structure that we wanted to talk about.